This use case is about the integration and validation of advanced remote driving functionalities in the open experimentation platform developed in the 5G-IANA project. The vehicle is equipped with an OBU front and rear camera, a LiDAR and a 5G modem for data transmission to the edge of the network. The teleoperation is possible thanks to a series of network apps, which have been deployed at the edge of the 5G network or the vehicle OBU, depending on its functionality. In the next phase, it will include advanced features such as 360 remote driving environment using VR glasses, enhanced warning service by integrating a 3D positioning algorithm using LiDAR data and AI detections that will provide driving assistance to avoid accidents.
A simulated version of the parking lot section at the Ulm testbed was created using satellite imagery. The road network is saved as both a 3D object and an OpenDrive file, facilitating usage of the road topology by services such as UC2's Maneuver Planner. Once in Unreal Engine and Carla, props are added for realism and the map is tested for consistency. Our Carla libraries allow users to create vehicles with a single line of code, choosing their starting point and the address of the OBU, real or virtual, to connect to. Other methods allow the user to define vehicle paths and switch their autopilots on or off. UC2's service chain in Cycle A consists of virtual vehicles running the MCAD Rover N app, which retrieves vehicle data and sends it to the edge using ETSI maneuver coordination messages. On the opposite side, MCAD Edge NApp, which uses vehicle information to compute the speeds they should maintain to traverse the intersection, instruct the vehicles in a timely and safe manner. Initial tests have been done with a single vehicle, with and without the UC2 service chain, to test proper communication between nodes. MCAD Rover was set up in a VOBU present in the testbed, whilst MCAD Rover was set up at the edge. Meanwhile, a Carla instance was running at the BILO premises and was connected to the Rover NAP. At the intersection, MCAD reduces the speed of the approaching vehicle. Future enhancements: creation of a graphical interface for the Carla plugin, multiple vehicle coordination with real AVs and subscription service.
Welcome to the 5G-IANA Virtual Bus Tour Use Case Validation Demo. Our objective is to demonstrate the entire 360 linear live streaming pipeline, utilizing the components from the first development cycle. First component in action is the privacy masking module to blur sensitive details. Then the live stream encoder handles the video encoding, compressions, and re-encoding tasks. Then the video stream cache buffers seamlessly the video stream, maintaining video fidelity. The active network monitoring module estimates the available network bandwidth through active probing, which is crucial for the live stream encoder. The use case specific log reporting service captures logs related to the tour, while the data broker exposes these data for monitoring purposes. Lastly, the video from the tour is streamed through the VR server module to the VR user. The setup consists of a camera mounted on top of a car, the onboard unit and a laptop inside the vehicle, and the mech server. During demonstration, we will retrieve data on 5G round-trip time, user data rate, end-to-end reliability, connectivity interruption time, end-to-end latency and service availability. Here we demonstrate the 5G connectivity and ensure the camera is seamlessly connected to the edge. The live stream flows from the camera to the mech at 1080p, with 30 frames per second and 9000 bitrate. Using network monitoring NApp, we'll connect to the endpoint via the browser and check the responsiveness of our endpoints. Inside the 5G-IANA bus, our VR user is gearing up for the experience. The VR server module comes to life, creating a seamless connection between the virtual world and our eager participant. Inside the bus, our VR user can engage with gestures, spatialized audio, and personalized avatars. Simultaneously, the log reporting service captures every moment for further analysis and optimization.
The 5G-IANA UC5 aims to develop a function for detecting hazardous driving events and transmitting warning notifications to nearby vehicles in real time. In this testing scenario, a vehicle that performed the hazardous events was mounted with a 5G-IANA OBU, while the vehicle that receives the notifications was a virtual one, equipped with a virtual OBU. In addition, an ML model creates clusters of harsh events to indicate areas of high risk. In the first testing, the real vehicle performs harsh acceleration and harsh braking events in the Helmerstrasse. The virtual OBU is facing north, as if trying to exit the smaller street and enter the Helmerstrasse. In both cases, an attention risk notification is displayed, as the notification is important to the virtual vehicle regardless of the real vehicle's heading. In this case, the real vehicle performs speeding events in the Helmerstrasse. The first time, no notification is displayed, as the virtual OBU is facing east, heading opposite the real vehicle. When the vehicle turns and speeds, an attention risk notification is displayed, as both the vehicle and the virtual vehicle have the same heading. In this case, the real vehicle performs harsh acceleration events in the Helmerstrasse. The first time, no notification is displayed, as the virtual vehicle is facing east, heading opposite the real vehicle. When the vehicle turns and accelerates, an attention risk notification is displayed, as both the real vehicle and the virtual vehicle have the same heading. In this case, the real vehicle performs harsh braking events in the Helmerstrasse. The first time, no notification is displayed, as the virtual vehicle is facing east, heading opposite the real vehicle. When the vehicle turns and brakes, an attention risk notification is displayed, as both the real vehicle and the virtual vehicle have the same heading. In this case, the driver of the real vehicle performs mobile use in the Helmerstrasse. The first time, no notification is displayed, as the virtual vehicle is facing east, heading opposite the real vehicle. When the vehicle turns and brakes, an attention risk notification is displayed, as both the real vehicle and the virtual vehicle have the same heading. Harsh events, accelerations and brakings are performed in the Helmerstrasse. The ML model creates clusters of harsh events in both directions. The vehicle enters areas of aggregated risk, created with mock data, and receives an attention risk notification in both directions when entering the risky area.
Introducing the Extreme Edge Orchestrator, or EEO, a key component of the 5G-IANA platform designed to manage the life cycle of processing and AI/ML tasks on extreme edge devices such as Vehicular Onboard Units, OBUs. With smart device selection based on a wide array of user-defined criteria such as device capabilities, real-time resource usage, and location, the Extreme Edge Orchestrator optimizes performance at the extreme edge. These lifecycle management policies are imposed via the Policy Executor module of the platform that utilizes the underlying Kubernetes framework to manage containerized applications on the OBUs. In the context of 5G-IANA, the Extreme Edge Orchestrator enables the operation of Use Case 6. Use Case 6 facilitates federated learning over the 5G network using Flower, an open-source distributed AI/ML framework. As such, the Vehicular Onboard Units collaboratively train a deep AI/ML model that is thereafter used to predict future instances of network quality of service degradation. The Extreme Edge Orchestrator constantly monitors the OBUs through the platform's advanced telemetry mechanisms. It therefore ensures smart device participation, adjusting nodes by adding, removing, or even rejecting them based on the user-defined criteria. At the same time, it features a graphical user interface that displays model convergence statistics, network resource consumption, OBU location tracking, as well as a notification board for system events, giving users a real-time view of the AI/ML progress.